So thank you for the organizer for inviting me to this wonderful machine learning summer school. Actually, this is the third time I lecture in the machine learning summer school. The first one was already there 14 years ago, maybe more than that, in 2007, yeah, actually, well, in Tübingen. And well, today, I'm going to talk about a kind of my recent work on the machine learning using the group theory. So as the introduction, well, because perhaps your background are various, including math and computer science and maybe the biology and so on. So I'm going to start with a very basic fact about the group theory. And I'm going to explain how group theory can be applied to machine learning methods. So you may know that we can see many types of symmetry in our daily life and in many aspects of our life. For example, we may see many symmetry in the design of something. You can see that this is the symbol or family symbol of the shogun in Edo era in Japan. And you can see a very beautiful symmetry. This is a cloister in the University of Glasgow. And as you can see, in design or architecture or some symbols, we can use a lot of symmetry in making something. Not only in design or some, well, artificial things, we can see symmetry in nature. For example, many living things naturally has symmetry. Human face has also the very symmetry. Human body has also the symmetry. And also in chemistry and physics, there are lots of symmetry existing in nature. You may know that crystal lattice has a very beautiful symmetry. And also you can see in physics that atomic configuration has symmetry, and the many chemistry theory and the physics theory make use of such symmetry in developing something. And you may also know that machine learning methods have been successfully applied to these areas of chemistry and physics nowadays, and they tend to use such symmetry in developing methods and theory. Okay, so in recognizing symmetry, we often see or we often imagine some transformations in the object. For example, in this butterfly example, you may see some, well, the flip in the horizontal direction or along the vertical axis to recognize the symmetry of this object. And also, if you are given this symbol, you may rotate in this way. So this is a kind of a rotational symmetry. And in the third example, you may apply some shape to recognize the symmetry. In this way, symmetry and the transformations are mutually very connected in the concept. And the symmetry is often recognized by such transformations acting on some objects. So mathematically speaking, this type of symmetry or associated transformation can be formulated as a group or symmetric group. And they are studied in a part of algebra, you may know. And on the other hand, group or symmetry is recognized nowadays as a core of geometry also. So traditionally, the group was studied in the part of algebra, but it was late 19th century that the Klein, well, hit on the idea that a group gives a very unified characterization of various geometry. At that time, there were several notions of geometry. The most traditional one is Euclidean geometry, as you know. However, there were and there are lots of other geometry called non-Euclidean geometry, such as Poincare disk or projective geometry. And it was puzzled at that time that what is a unique geometry and what is the characterization of such geometry? And at that time, Klein introduced the notion of transformation by groups to characterize such geometry. And it was a very strong impact on the geometry as well as mathematics at that time. And since then, the group is one of the geometric concepts also, as well as the algebraic concept. Okay, if you think about machine learning, obviously, machine learning deals with data. And the data often has some geometry. So it is natural that we can make use of symmetry in the geometry of data or the group theoretic consideration in the geometry of the data. For example, this is perhaps a very popular example of the symmetry in data. In object recognition or classification, any shift or rotation should give the same class label. In this case, they should be categorized as cat, irrespective to the location or rotation. And to consider this type of geometry of data or symmetry of the data, machine learning methods have been developed in various ways. And there are two popular approaches to consider such symmetry. One major approach is data augmentation. Let's say we have some data and we want to make a classifier irrespective to the location and the rotation. Then let's prepare the augmented data by acting shifts or rotations to one data and make a class label cat in the same way. And this is the augmented training data. And we train the classifier with the augmented data to make an invariant classifier to such rotation or shifts. This is a very popular approach and very understandable. And here's another approach. This is a kind of architecture approach to the symmetry. Instead of data augmentation, people consider the architecture that embeds the symmetry in the model. And the celebrated method is a convolutional neural network, which is already dated back, well, like more than 20 years ago. So here's the aims of this lecture. I want to explain how machine learning method handles this type of symmetry in data or the symmetry in the geometry of data. And I'd like to explain how the group theory handles such symmetry in the machine learning method. And because of the constraint of the lecture time, I will not give a very comprehensive review of the existing researches on this direction. But I selected the topics and confined such topics to give you some basic idea of those methods. And as a primer to the machine learning group methods, I first give a very basic mathematical theory on groups as a foundation to develop or understand the various methods using groups in machine learning methods. And in the second part of my lecture, I'm going to talk about the convolutional neural networks, basically. And especially recent development consider the group action and the group equivariant convolutional neural network. And in the last part of my lecture, I'm going to talk about more recent development, well, to the group theoretical method in machine learning. And this is an equivariant learning of representation of learning. And it uses the group theory, especially group representation theory, for the purpose of representation learning. I will cover this topic in the last part of my talk. Okay, here's the outline of this lecture. So I have already done the introduction and explained symmetry and machine learning. And in the next, well, perhaps 30 or more minutes, I will give you a very brief introduction of group theory, as a mathematical background to understand the convolutional neural network and the representation learning with group actions. And after such mathematical foundation, I will explain what's a group convolutional neural network and how it is used in practice. And in the fourth part, perhaps in the second half of my lecture, I will explain again the group theory, focusing on the group representation, and explain its connection to Fourier transform. And the last part of my lecture is somehow the research level topic, which I'm currently being involved. And I'm going to explain the representation learning through group action and the group representation. Here, the word representation is used in two meanings, actually. I'm going to explain the details later, but group representation is a mathematical concept, and the representation learning in the machine learning terminology. The same word is used here. And I'm going to talk about the representation learning with group representation. Maybe a little bit confusing, but anyway. Okay, so I'm going to going into the group theory as basics. So as I explained, so symmetry or associated transformation to capture the symmetry are formulated as group mathematically. And here's a very basic definition of group, mathematical definition of group. Okay, I start from the very mathematical definition. So group is the set with binary operation. Operation is simply the multiplication or addition depending on the context. And it satisfies the following three properties. The first one is associativity. Perhaps you may be familiar with associativity in connection with addition or multiplication of real numbers and integers. And their identity, the existence of identity, sorry. So there should be some element which serves as an identity. So multiplication of identity with any element is the same as the original element. And the third condition is the existence of inverse. So if for any element in group G, there should be an inverse element. And the multiplication of A and the inverse of A should be identity. This is just a generalization of the inverse number. If we have a real number, then non-zero real number, we have an inverse element. And this is just a generalization. So in practice, you can imagine the real number or the complex numbers as are very typical cases of groups. Here are more examples. Okay, I have already explained, sorry. So non-zero real number is a very simple example of group under multiplication. Operation is just a multiplication. This is very clear, right? And also, as a terminology, this is called a commutative group because AB and BA are the same. But as I will explain, this is not always true in the general group. And this is again the terminology, but the commutative group is also called abelian group in some, I often use abelian group to call the commutative group. And another popular example is integers, or the n times, well, Cartesian product of integers, or the Euclidean space, n-dimensional Euclidean space. And they are abelian groups under additions. You can see that this is abelian because a plus b is equal to b plus a. Okay, very clear. And in the case of additive, we call this additive group because in these examples, instead of the multiplication symbol, the additive symbols are often used. So the plus symbol is often used. So in such cases, we call them additive groups. And also, by convention, the identity element is denoted by 0 for additive groups. This is just a convention. And the inverse element is represented minus a instead of a inverse. This is also just a convention. Okay, here are other examples. So this is a finite group, which means we have only finite number of elements in a group. So this is the simple group of integers, but the modulo n. So if you consider integers modulo n, that makes additive group. Perhaps you may be very familiar with this type of concept. And well, if we add 2 elements and take modulo n, and we have an element within this element from 0 to n minus 1, and we can make a group. And 0 element and inverse element exists here. And this is often denoted by z sub n. And this is called a cyclic group because if we add an element n times, then it comes to the same element. So this is called cyclic group. But in some context, this cyclic group Zn is considered as a multiplicative group locating the element on the unit circle in the complex plane. In that case, an element can be written in this type of notation using the complex number. I is the imaginary unit. And in this case, this complex number can be multiplied, and we have n elements, and the multiplication gives another element within this set. And this is well, another expression of the same group of Zn. Okay. So far, I have talked about only the abelian group or commutative group. The A times B is equal to B times A. However, there are lots of examples of non-commutative group also. Here is the most popular example called the general linear group. This is just the set of non-singular matrices of the size n times n. This is denoted by GL, general linear group, dimension is n. And as you may know, because of the non-singularity in the definition, we have the inverse element, of course, and identity matrix serves as the unit element or identity element. So this makes a group, but you know that this is non-commutative group if the dimension is equal to or larger than 2. Because as you know, in general, the matrix AB may not be equal to matrix BA. So this is a group, but it's not necessarily commutative. Okay, I will continue a little bit more basic definition on groups. The first one is subgroup. This is very simple. So if we have a group, and if the subset is again makes a group, then we call it subgroup. The operation is closed under this subset H. In that case, it makes a group and called a subgroup. And sometimes I use this notation to denote the subgroup. And here are a couple of examples of subgroup. This is also very simple. They are mathematical exercise, but so in the group of integers, the multiples of m makes a subgroup. This is quite simple. The multiple of m consists of group again. So this is subgroup of Z. And another example is a subgroup of the cyclic group Zn. Okay, here's the example. If we consider Z sub 6 and take an element 3 and 0, then these two elements makes a group because 3 plus 3 in Z6 becomes 0. By taking modulo 6, we see that the 3 plus 3 is 0. So this makes a subgroup of two elements within the group of Z sub 6. Okay, this is also a very simple example. And another very important example is orthogonal group. Orthogonal group is consists of orthogonal matrices of size n, and they makes a group because the inverse identity exists in this orthogonal group, and the inverse is also orthogonal matrix. So this makes a subgroup of general linear group. And also SON, this is our special orthogonal group, meaning that the determinant is 1. So in orthogonal group, there are rotations and reflections. However, SON consists of only rotations in the n-dimensional space. And they are example of subgroup of general linear group. Okay, this is also the very simple the notion of direct product. Direct product is a way of making another group from the two groups. This is quite simple. This is as a set, this is just a Cartesian product. And also the operation is component-wise. And this makes a group. This is just a simple construction of a new group from two groups. Okay. Another notion is a mapping of groups. It is called homomorphism of group. Let's say that we have two groups and a mapping from G1 to G2. Then we call it homomorphism if the group action is maintained in this operation phi, in this mapping phi. Okay, here's one example. If we consider the mapping from Z6 to Z3, okay, Z6 is our integers modulo 6, but we can consider the integer modulo 3. So in this case, modulo 6 is converted to modulo 3, and well, the correspondence of the element is given in this figure. So 3 is there is mapped to 0 because in modulo 3, the integer 3 becomes 0, and 4 becomes 1, and 5 becomes 2. And this is actually the homomorphism, keeping the group operation. In this case, that's just addition. And I want to introduce, the isomorphism here. So isomorphism is a group homomorphism, which is also bijective. In that case, we call it isomorphism. And if there is an isomorphism between two groups, they are essentially the same because the number of the elements is the same, and the group actions are exactly, group multiplication, group operation are exactly the same. So they are basically considered as the same groups. Here's one example. Okay, G6, which is an integer with modulo 6, is isomorphic to G2 times G3. Well, this may not be very trivial, but in fact, if we consider, so the G6 is a modulo 6, but we can take modulo 2 and modulo 3 respectively. And if we take the product, direct product of modulo 2 and modulo 3, and they make a group homomorphism and also bijective. So we can see that the G6 is isomorphic to G2 times G3. And more generally, the G sub n is decomposed in the direct product of Z something. This is the general result of finite abelian group. Okay. So I'm going to explain more the important example used in developing the machine learning methods. So first one is symmetric group. So the symmetric group is a group of all the permutations of n items, and the Sn denoted by Sn. N is the number of items. And it is very easily confirmed that the symmetric group is non-commutative if n is equal to or larger than 3. And you know that the number of all the permutation is n factorial. Okay, let's look at the S3 very closely. So there are 6 elements in S3 as a permutation of 3 items. And it is important to note that the S3 contains G3 or C3, the cyclic group of 3 elements. Okay, let's look at this element in permutation of 3 elements. 1 is moved to 2, and 2 goes to 3, and 3 goes to 1. This makes a cycle, right? Geometrically or graphically, we can see in this way: 1 goes to 2, 2 goes to 3, 3 goes to 1. And this can be interpreted as a rotation of degree 120, right? And so there are 3 times application of this the permutation gives the identity. So in this way, this element in S3 makes a subgroup that is the cyclic group of 3 elements. And in S3, here's another element, tau, which I call tau here. And this corresponds to reflection. And sorry, this is the flip of 2 and 3. The element 1 is fixed, and the 2 goes to 3, and the 3 goes to 2. So geometrically, this corresponds to the flip of 2 and 3 in this way, along the vertical axis. And you may see that this is a kind of reflection in the 2-dimensional Euclidean space. And you can see that these 2 elements generate the group of S3. You can see that the 6th element. After applying reflection, we can also apply the rotation 2 times, and these 6 elements makes the S3. And you can also see under application of successive application of sigma and the tau makes the sigma and the tau makes the permutation 1 goes to 3, and 2 is fixed, and 3 goes to 1. Okay, so from this one, if we swap 2 and 3, then we have this element. However, if we first flip the 2 and 3 and apply sigma, the 120 rotation, this element is different from the previous one. So the tau sigma and sigma tau are different. That is the easy example where we can see the non-commutativity of the symmetric group of element 3. Okay. And another very important example of group is Euclidean motion. So Euclidean motion is, by definition, the isometry of Euclidean space Rn. N is just a dimensionality of the space. And well, it is not very difficult to show that the Euclidean group En consists of the composition of rotations and translation and reflections. This is a very simple exercise. And so we can write the Euclidean group as a combination of rotation and translation A, where rotation R is an element of the orthogonal group On. This consists of the rotation and the reflection. And the shift A in our Euclidean space. This is just a vector corresponding to the translation. And also, I'm going to use a special Euclidean group. This excludes a reflection from En. So this consists of just a rotation and a shift, or translations. And we can also see that En or SEN are in general non-commutative group. Okay, let's look at the example of SE2, the two-dimensional Euclidean motion, very closely. Okay, first, let's see what happens if we apply 2 elements or multiply 2 elements. The first element is a rotation by theta and apply the translation A. And the second element, rotation eta, and apply the translation B. And R theta is simply the abbreviation of the two-dimensional rotation by angle theta. Okay, first, applying R theta A, this element, moves this triangle to this position. Well, first apply the rotation in this way, and apply shift by A in this way. We have this location to the triangle. After that, we apply the second element, R eta B. Then we apply the rotation R eta first. We need to notice that this whole thing should be rotated. So this shift A must be also rotated here, depicted in this green triangle. And then apply translation B. So the yellow triangle is a result of the successive application of this element and R eta B afterwards. So in total, we can see the rotation part is simply the eta plus theta. This is well, because SO2 is commutative, we just see that the rotation part is gives just the addition of the rotation angles. However, to the translation part, we see that this A is also rotated by angle eta. So in addition to B, we have an element R eta A, right? So this is a result of the multiplication of two elements of SE2. You can see that this is non-commutative because R eta appears in this translation part and A appear in this way. So if we swap R theta A and R eta B, then we have a different vector in the second part as a translation part, right? So this is another example of a non-commutative group. Okay, and also we have a very simple the matrix expression of the En in general. If we make a n+1 dimensional matrix, A is a rotation matrix taken from On, and A is a vector for the translation. And for the mathematical convenience, scalar 1 is added here, and 0 is added here. 0 vector 0 is added here. This is a row vector, right? And if we multiply two elements of this form, we observe that this part is just BA, and this vector part is BA plus B. And this corresponds to the this element we considered by this graphics, the picture. And in this way, SEN or En in general can be expressed by this, well, the matrix notations of dimension n+1. And this is very convenient, and I sometimes use. Well, may not be used so often, but this is very popularly used in literatures. Okay. So I will introduce to look at the non-commutative group more closely. I would like to introduce the semi-direct product, and for this purpose, I will introduce normal subgroup. Normal subgroup is also a very important class of subgroup, but for the purpose of this lecture, I just briefly explain what is normal subgroup. Normal subgroup is a subgroup, but for arbitrary element G, this type of element, which is often called conjugate, is also included in the subgroup. H is taken from the subgroup, and G is arbitrary element within G. And this, the stability of the subgroup by the conjugacy operation is used as a definition of normal subgroup. So in short, the normal subgroup is a class of subgroup which is stabilized by the conjugacy operation. And I'm not going into the details about this part, but if you take the coset by dividing n, well, I'm not explaining this one, but well, if you are familiar with the coset, then this can have naturally the group structure again. And I will explain the more detail in the appendix. And also, as you can see that if the group is commutative, then G and H can be swapped, and the G times G inverse is identity. So this is again equal to H. So that any subgroup in a commutative group or abelian group is just normal. So the normal subgroup is a kind of well, we can consider the non-commutativity by considering the normal subgroup. Okay, let's consider the normal subgroup of Euclidean motions. In the Euclidean motion, we have two elements, rotation part and the translation part. And if we consider the translation part only, they make a normal subgroup of Euclidean motion. Okay, so the translation part, the translation subgroup can be expressed in this way in the n+1 matrix notations, because the rotation part is just identity. And we apply just a shift to the existing the vector. And if you take a general element from En and multiply inverse under this element, and the simple calculation can derive that this is again just a translation, A times B. This is somehow very intuitive by the geometric consideration also. But in this way, we can see that the translation is a normal subgroup within the Euclidean motion group. And if we take the coset, then that is the remaining part, or the residual class gives the orthogonal matrices, just this part of the Euclidean motion. However, we introduced the Euclidean motion as a pair of rotation and translation, but they are not commutative actually. In that sense, the Euclidean motion is not a direct product of the translation and the rotations. Instead, they are given by a semi-direct product. I'm going to explain the semi-direct product very briefly in the next slide. So in many cases, for describing non-commutative group, we may have the expression by a pair of two simple objects like rotation and translation. However, as we saw in the example of the Euclidean motions, they may not be the product group, direct product group, but sometimes they are in the class of semi-direct product. So the formal definition is slightly involved, so I'm going to explain the semi-direct product somehow intuitively. So let's use this example. We have seen several times the symmetric group S3, and they are actually the semi-direct product, not a direct product between G3 and G2. So we see that there is a subgroup G3 within the symmetric group S3. And also the reflection, in this case, the flip between 2 and 3 makes a subgroup of the two elements, right? This is just simple. The inverse is, again, the tau in this case. And we can see that if we apply the tau inverse sigma tau, then this becomes sigma 2 times multiplication of sigma. So first we sign flip, the flip between 2 and 3, vertical, the horizontal flip, and apply the rotation, and flip back again. And it makes not the rotation of the same angle, but the rotation to the backward angle. So this is exactly the 2 times application of 120-degree rotation. So application of this conjugation gives somehow the change within this subgroup of Z3. This is not identity mapping, but there are some, well, group isomorphism actually of Z3. And this, well, twisting, of sigma by tau makes some, well, isomorphism of Z3. This type of twist explains the non-commutativity, of course, and also they're used as a definition of semi-direct product. In the semi-direct product, if we apply the twist of tau, the twist of sigma by tau, it makes not the identity, but some translation within Z3. So that explains the non-commutativity of this pairing of sigma and tau. Here's another example. So we can see that R2 is a normal subgroup of SE2. In that sense, if we apply this conjugation operation by rotation matrix R theta, then the translation A becomes a different element within translation. And that is actually the R theta A. If you apply rotation by angle minus sigma, and apply translation A, and apply the rotation back to the angle theta, it makes the translation R theta A. And this is again the transformation within the translation subgroup, normal subgroup. And we can see that this is non-commutative, but this type of conjugation gives how they should be computed in a non-commutative way. So existence of this type of conjugation gives a notion of semi-direct product. This is a paired, this is a kind of the paired data or Cartesian product of two groups, but they are not commutative, but the multiplication operation can be computed using this conjugation operation. This is the meaning of semi-direct product. Okay, so I think, well, I have so far talked about only the group theoretical concept, and maybe, well, you are a little bit tired of algebra. So I'm slightly coming back to machine learning or geometric part. Okay, based on this notion of group theory, let's consider the more geometric or machine learning concept. Let's consider first a group action on the space or data space typically. Okay, we have a group and X is a set, which is basically regarded as the space of data. And the action of a group is a mapping of the very formally, the group element and the element in the data space makes another data. And we say this is action if the identity element makes identity mapping of the space, and the group action successive application of element G and H gives the successive application of the mapping. In this case, X is mapped by G, and then that point is mapped by H. And the second one is very important in considering the group action. Group action, the mapping and the group multiplication are compatible. That's the meaning of this second condition, assumption. So because for the notational simplicity, I often use the circle symbol to denote the group action. And in that sense, if we apply identity element, then X is fixed. And if we multiply G and H successfully, and this is simply the application of H and G. That is a very simple idea that you can see that the matrix and the vector, for example, they are special example of action. Okay. Sorry, this part is a little bit, well, sorry. I haven't defined the group representation here. Sorry, it remains, but just well, neglect this part. Okay, let's talk about invariance equivariance, which is often used in machine learning literatures nowadays. So the invariance, let's say that the group is acting on some two sets, X and Y, the same group acting on two sets, X and Y. And we have a mapping phi from X to Y. Then the phi is called invariant to the group action if the action of the group doesn't change the target value, the ending value by phi. This is invariance. And equivariance requires that the mapped point, group action is compatible or commutative with the mapping phi. In this case, if X is mapped to some element, that this new point given by the group action is mapped to an element which is given by the group action of the same element from the mapped data point phi of X. So mathematically, the equivariant is defined in this way. Okay, so invariance and equivariance are often, the notion of invariance and equivariance are very important in machine learning. For example, if you consider the object classification, then let's say that this is a bedroom and it should be classified as a bedroom in object classification. In this case, any translation or maybe rotation should give the same class label. This is saying that the classifier should be invariant to the group action of shift. Also, equivariance is often considered in various machine learning tasks, especially the image processing tasks. Let's consider the segmentation tasks. Then, if we have this image, we have the segmentation of the image like this. If you take a shift from the original image by some amount, then the segmentation result should be shifted to the same amount. This is a desired property of the segmentation of images, right? And in this case, we require the segmentation mapping to be equivariant to the group action of shift. Okay? And so there are various machine learning techniques which make use of the invariance or equivariance by some group actions. So actually, various data, including images, have symmetry. In the case of images, they are shifted. Naturally, the image has a group action of shift, and rotations also, two-dimensional rotations also. And also, we have sometimes spherical data, like the three-dimensional images or the panoramic images. In that case, we may have the three-dimensional rotation applied to the image. And also, the graphs has a permutation applied to the nose or sometimes the edges to the naturally such a graph action, the group action can be considered. And incorporating such type of group action and symmetry into the machine learning methods should have various advantages. Especially, this method considers the compact representations in some sense. For images, such type of group action may give the low-dimensional effective expression of data. And also, in terms of the model architecture, we may be able to make smaller models by incorporating such group actions or group symmetries. So in this way, various techniques can be considered. And as I talked in the beginning of my lecture, so one very natural and still popular approach is data augmentation. If we have some group symmetry in the data, then we can apply the various such group action to the data and train the neural network with such augmented data. And this approach is very popular and they're easily extendable to non-group cases also. That's one advantage. And however, it requires lots of training data. And also, there's no theoretical guarantee that such data augmentation can really acquire the invariance or equivariance of the mapping. And the second approach is the architecture, as I explained in the first part, at the beginning of my talk. And the equivariant neural network, which is basically the convolutional neural network, and recently group convolutional neural network have been developed. And such approach is becoming very popular when some group symmetry exists in the data. And in this case, we impose a symmetry or group action in the architecture of the networks. So we have a very the compact expression or compact modeling of the symmetry. And also, as I plan to give explanation in the last part of my talk, the representation learning can be also used, there can also use such type of group symmetry, incorporating especially equivariance of the mapping, which expresses some group symmetry of data. Okay. So in this lecture and in many literatures of machine learning, equivariance is more focused than invariance. And there are a couple of reasons for this. So first thing we should notice is that invariance can be easily achieved if we make an equivariant neural network. Because let's say in the convolutional neural network, we have many layers of that realize the equivariance. And if we apply some invariant mapping or invariant layer at the end of the architecture, then total mapping becomes invariant. So it is more important to consider the equivariant part than making an invariant part. And the invariance of this construction using equivariant plus additional invariance, it can be easily confirmed by just using the definition of invariance and equivariance. And also, invariance is a very special type of equivariance. We can also interpret it like this. Let's say that we have x and y, and group G is acting on x. And let's make a trivial action of G on y by defining the action by the identity for any element of y. And then equivariance to this mapping, meaning equivariance of this mapping, meaning that this is just an invariance. So for these reasons, the people often talk equivariance rather than invariance. And let's consider the equivariance. And before talking about the group convolution, sorry, the group convolution neural network, I would like to introduce, well, another notion which is very useful in developing machine learning method. That is called group representation. This is perhaps the final part of the group theoretical part 1 in the first half of my lecture. So the group representation is simply the linear group action. So here is a couple of motivations in considering the linear group action or group representation. So as we see that the group is a very complicated object sometimes, especially if, in the case of non-commutative group like ON or symmetric group, the structure of a group is very complicated, and there is no very easy way to understand the whole structure of group. However, mathematicians have developed a very nice idea of converting this complicated object to linear algebra. That is called group representation. And by this method of group representation, various the complicated or the difficult problem on the group can be converted to linear algebra or matrix theory. That is a virtue of group representation. I will give a formal definition later. And there are some typical cases. And for finite group, the group representation has been developed extensively. And for abelian groups, the group representation is essentially corresponds to the Fourier analysis. I will come back to this point later. And also for compact groups, we can generalize Fourier transform almost exactly to the non-abelian cases. And also, I will not going to cover this type of group, but there is the very special type of called Lie groups, which has a very beautiful theory in combination of manifold theory and group theory, but I'm not going to explain this part. Okay, I will give a formal definition of representation. Let's say we have a group, and V is some vector space, and GLV is just the invertible linear transformation, like GLRN in the case of the vectors, the Euclidean space. And the group representation is simply the mapping from group to the invertible linear transformations, so that the group multiplication is mapped to the matrix multiplication. So the element AB should be mapped to the multiplication of two matrices, row A and row B. This is the definition of group representation. And if we multiply some vector to this matrix row of A or row of A, B, then you can see that this is exactly the same as the definition of group action given by the linear matrices in this case. So as I explained here, so group representation is simply the linear group action acting on some vector space. Okay, this is some trivial things. I skipped this one. And this is just a real terminology, but the dimension of V, this vector space, is called the dimensionality of a degree of the representation. And in many cases, I just, well, in this lecture, I just consider the finite dimensional space for V, but may not be true, sorry. Sometimes we should consider the infinite dimensional vector space as this V, especially the functional space. Function space may be considered as this vector space V. Also, in connection with the Fourier transform, this V may be a complex vector space, but this is a simple extension. Okay, let's consider some example of group representation. Again, I use the symmetric group acting on 3 items. In this case, as a generator, we have a row, the rotation of 1/3 of the 360 degree, and the flip of 2 and 3. And geometrically, they can be written in this way. Okay. And we have 6 elements, and want to make a map from these 6 elements to a matrix. But actually, this graphical or geometrical expression of this group S3 is already defining our group representation in this case. Let's take just a 2-dimensional group representation here. And for sigma, let's consider the 120-degree rotation as depicted in this figure. And for tau, the mapping of tau by rho is given by the flip along the vertical axis. So in terms of the 2-dimensional matrix, this is just the inversion, the minus for the x-axis, x coordinate, sorry. And this is an example of group representation. You can see that this graphical interpretation of S3 is confirming that this is actually the satisfying the definition of group action, the group representation. Okay. So this is another type of representation, which is very useful or important in defining a convolutional neural network. This is called a regular representation. The name is very, well, may sound fancy, but this is simply the shift of function. This is called a regular representation in group theory. Okay, let's think this function on some space. And assume that this space has some vector, the group action. Sorry, okay, just a moment. Okay, so, well, okay. In considering regular representation, sorry, let's consider the function space on group G. This is a vector space. This is maybe an infinite dimensional vector space if G is infinite dimensional space. Sorry, the continuous space, sorry. But we can consider this as a vector space because addition and the scalar multiplication can be easily defined by the value of function. And we can define the group action or representation in this way. This corresponds to the shift of functions by G. Let's consider the simple example of R and their function on R. R is the additive group, and the shift is the group action or the group operation. If we shift the function by A, the correspondence function can be defined in this way. You may think that the G inverse may look a little bit fancy. Why not the G? But this inversion of G naturally appears if we consider the shifting function f. If we shift the function by A in this case, if we want to evaluate the function value of shifted function at location x, then we should look at the value of x minus a of the original function, right? So we need to make our inversion here to recover the value of the original function. In this way, this is just a shifted function, the shift of function. But mathematically, this is a correct way to define the function the shifting of the function. Okay, and it's very easy to confirm this is a linear operation on the space of V, and also they satisfy this definition, the assumption in the definition of the group representation. So this is one example of group representation. There again, the vector space is the space of function on G. And this is called the regular representation. Okay, in introducing convolutional neural network, I often use this regular representation. So just memorize this terminology. Okay, so maybe most of the parts are just math, sorry. But I have already prepared the basic group theoretical aspect to explain the group convolutional neural network, and also the basic the ideas to define the representation learning. So in the next part, I'm going to explain the group convolutional neural network. Okay, let's consider convolutional neural network. So maybe you have heard about convolutional neural network. This is one of the most popular models, and before transformer, this is a de facto standard for the image processing, and still people often use convolutional neural network as a starting point of image processing. And the convolutional neural network is already like 25 years back, and the earliest neural network model to realize translation equivariance. And it uses a convolutional layer and a pooling layer, and it is trained by backpropagation. And I'm going to explain what is convolutional layer from now on. And this architecture is actually inspired by the biological neural network of early visual cortex. And actually, before the proposal of Yan Lucan or the Wei-san in the late 80s, the Japanese researcher Kunihiko the Fukushima proposed the model which uses a convolutional layer and the pooling layer, which is called the neocognitron. But unfortunately, at that time, the backpropagation was not well invented, not yet invented at this error. This is just a 1979 or 80 when the Fukushima proposed the neocognitive theorem. And the backpropagation was like several years after this age. So the learning of this neocognitive theorem was a little bit difficult, and practically it was very competitive to recognition tasks. But however, the architecture and the basic idea was dated back to this era of neocognitive theorem. Okay, so let's review the standard convolutional neural network. I start from the convolutional layer. So convolutional neural network is basically the model for image processing. So the signal in the input layer is a function of the pixel. In the simplest case of grayscale images, this is the real valued or the scalar valued function of pixel. And the convolutional layer applied some spatial filter of small size to each part of the input signal. More mathematically, let's think that the spatial filter is 3 times 3, like in this picture. Then we shift the spatial filter to compute the output value of at the pixel I and j. We shift the small spatial filter by I and j, and takes the inner product between the filter value and the signal values. And usually some nonlinear mapping like sigmoidal function is applied to the output. And it is often the case that for notational simplicity, we regard that the spatial filter takes a value 0 beyond the border of 3 times 3. And in that case, and instead of describing difficult notations, we just take the sum over the whole area of Z2 square, and that should be fine. Just 0 beyond the border. And in the case of color images, the functions are 3-dimensional value, taking the RGB values. And it is often called nowadays the channels. So we have 3 channels as the output of the function of signal. And in this case, because taking the shift of the color doesn't make sense, people just consider the inner product of the color directions, and only the spatial directions, they apply the shift. And it is also very popular that after taking the convolutional layer, people often apply pooling layer, which the aim of pooling layer is to take the subsampling or downsampling to shrink the dimensionality of the expression smaller. And in this way, the one typical example of pooling layer is to take the maximum value within, for example, 2 times 2 area. And in this case, the spatial size of the signal shrinks into 1/4 of the original one, dimensionality. Taking max is called max pooling, and there are also other type of pooling like average pooling and L2 norm pooling, and I will not go into the details, but because the spatial dimensionality is shrinked, people often use larger number of channels instead to keep their expressional power. And also at the final stage of convolutional layer, people apply the fully connected layer. This is just a standard fully connected multi-layer perceptron, and a whole model is trained to acquire the invariance or equivariance hidden in the layer, hidden in the data. Sorry. Okay, that's our basic fact about the convolutional neural network. And the convolutional neural network achieves translation equivariance. Well, I explain this one. I will using this figure. So the convolutional layer applies a spatial filter after shifting. And the translation equivariance means that if the original signal is shifted, then the output is shifted to the same amount. Okay, here is some mathematical proof of this fact, but geometrically or graphically, this is quite simple and obvious. That if the signal is shifted like this by some amount, then the shift of the pixel compute exactly the same manner using the spatial filter, right? This is obvious. So the equivariance of convolutional layer is almost obvious. In terms of the symbols, well, we can write in this way. This is a kind of definition of equivariance. But our intuitive explanation will simply let you understand the translation equivariance of convolutional layer. And applying the activation function is simply the change of the value. So the equivariance is obviously satisfied. And the pooling layer is a little bit complicated because it shrinks the spatial size. In that case, we need to consider the different group action to the reduced spatiality. If the original signal is shifted by 2 times 2 max pooling, for example, we need to consider only 1 pixel shift in after the pooling layer. But in this modification, we can see that the pooling layer also satisfies the equivariance. Okay, in this way, the pooling layer, the convolutional layer and the pooling layer achieves the equivariance of translation as a group action. And as I explained in the middle, the application of the invariant layer at the as a final layer of the architecture, we can obtain the invariant classification. So building equivariant layers is important in the definition of convolutional neural network. I will come back to the group equivariant convolutional neural network part. So after understanding the traditional convolutional neural network, it's not very difficult to extend it to group equivariant convolutional network, well, with the knowledge of group theory. So you can see that this is the standard group, the convolutional neural network. And in the case of convolutional network, the spatial, the space is just like the Z2 square, characterizing the space of pixel, and the output is like the RGB in the input space. So R3. And the equivariant layer, so the group operation here is Z2, the additive or translation operation. And the equivariant means that shifting F and applying the convolution layer is equal to taking convolutional mapping, applying convolutional layer and shifting after that. This is equivariance. And group convolutional neural network considers a function from group to some Euclidean space. This can be RGB, and this can be, well, other type, well, any dimensional the channel direction. Basically, the channel. And the equivariance means that after some group action, regular representation action, well, regular action actually, there are like a rotation and the rotation and the shift. There are convolution after taking the group action is equal to the convolution after, sorry, their group action after the convolution. That's the meaning of the equivariance. So how to make, before, well, the building blocks. So there are some motivations that are group action is extended to group the general group from the translation. Obviously, there are many image property are invariant not only to translation, but more general Euclidean motion. The typical example is medical images. In the medical image, the orientation doesn't make so much sense in general. In the natural images, like the rooms and the roads, the orientation may have some meaning. Like so we have a, well, basically we don't have an image of the road on the top and the sky in the bottom. But the medical image doesn't have such meaning in the orientation. So the rotational or Euclidean motion invariant classifier should be very useful. And also nowadays, we have many images of 3D and the panoramic images of 360 degrees. The three-dimensional rotation or three-dimensional Euclidean motion may be useful to consider. I will not cover the graphs in this lecture because Ryoma Sato gave a lecture on graph neural network in the last week. So, but for graphs, the permutation invariance for nodes may be important. And also, if the graph is considered in the three-dimensional space, like the molecule in three-dimensional space, the Euclidean motion is again the very important factor to consider. So let's look at the model of, or the architecture of group convolutional neural network. So I explained the example of typical groups to be considered in group convolutional neural network. And this is taken from the original paper, and I'm not sure if these notations or the names are popular in many other fields, but P4 is 90-degree rotations and the translations. So this is a subgroup of SE2, two-dimensional Euclidean motion. But the rotation part is simply consists of 4 elements of 90, 180, and 270, and the 0-degree rotations. And as in the case of SE2, this is a semi-direct, the semi-direct product between the Z2 explaining the shift and the SO24. SO24 is a 4 discretization of SO2. So the 19 degree and the multiple of that. And the P4M is simply the addition of a reflection to the P4. And this is again the semi-direct product. Okay, so let's again consider the general group. And in this case, the signal is a function from group to some dimension specified by the channel numbers. And in this case,
So this is just a shift group translation of the filter. We have the filter for the space. And this is just a simple generalization of the standard convolutional neural network. And if we use the terminology of the regular representation, this is a shift of the function denoted by L sub G, and just the inner product using the group element, because the base space is a group in this case. And well, if we take the function value at G in the output, then we just apply the shift of by G to the filter and just take the inner product. This is the same as the standard convolutional neural network. And in the case of the input layer and the final layer may take the very special equations, because in usually the input layer is like image. So again, this is a function from Z2. But if G acts on Z2, the space of the pixels, then we can easily extend this definition to using the group action on the Z2. This is a straightforward generalization. So I skip it. Okay. So here's some illustration of the group convolution layer and the equivalence achieved by the group convolution. And this is the input image. And if we rotate by 90 degrees, we have this image. And both are inputted to the convolution layer. And then we have 4 images by the rotation. The shift is omitted here. And okay, so the group convolution I explained in the last slide may be applied to here also, but here is also the group function of the group to the function of the group. And actually, as I explained in the next slide, the group translation is commutative with the convolution, the mapping of the convolution group convolutional layer. So mathematically, equivariance can be formulated like this. The shifting operation by group element G after convolution layer is equal to the group convolution layer after taking the shift in the input signal. So I skip the mathematical proof here, but using this expression of the inner product with the shifted filter and the input signal, then we can easily see that this equivalence relation mathematically holds in general. And the useful lemma is that because we use the inner product here, we can confirm that the inner product satisfies this relation. If we apply the shift to F, this inner product is equal to the inner product of shift of inverse to phi with F. Using this formula, it's easy to see that this equivariance of general G convolutional layer. We can derive more directly, but this is a useful lemma to consider the G convolutional layer more mathematically. Okay, anyway, so the G convolutional neural network is simply very straightforward generalization of the standard convolutional neural network. And I will show some application of G convolutional neural network. The first one is rotation MNIST. This is a synthesized data by rotating MNIST, the handwritten digit data with random angles. And we have this type of data. And we want to classify the rotation invariant classifier to this one. And apply the rotational equivariant convolutional neural network. So this is the paper, the first paper that proposes the G convolutional neural network, and they apply the P4. This is the shift and the 90-degree rotations. You can see that in comparison with the standard CNN is here, G2 CNN. For the rotational element, of course, the standard CNN doesn't consider the rotations. So it's not surprising that the rotational convolutional neural network outperforms the standard one. But the standard one, the performance gain is like the error becomes almost less than half of the result given by the standard convolutional neural network. And interestingly, using the pooling layer, rotational pooling layer gives a worse result than the convolutional neural network without pooling layer. This is because the rotational pooling takes the average over the rotations. That reduces the equivariance performance and gives a worse result in this case. Okay, here's a more practical example of medical image analysis. And this, I take the result from this paper. And this is the application of SE2 equivariant convolutional neural network to 3 types of medical problems: mitosis detection, the nuclei segmentation, and the tumor detection. And in this case, as I explained, the rotational invariant or equivariant should be important because rotation doesn't make any sense to medical images. And in this case, they consider a couple of candidates of rotation discretization, and they test, well, sorry, they're very difficult to see, 4 discretization, 8 and 16. And the baseline to compare is, well, there are 2 baselines. One is data augmentation by applying the rotation and the shift. Sorry, in this case, rotation. The other one is the convolution, the standard convolutional neural network for only shift. And this is their detection accuracy, so their upward result is better. You can see that in comparison with standard convolutional neural network, the rotational convolutional neural network works always better. And the different color indicates a different amount of training data. So red one uses all the data. And you can see that in this case, data augmentation shows, well, somehow good result in these 2 cases especially. But still the best result among choosing the best choice of the discretization, the performance of the group convolutional neural network shows better. And a more interesting result is the invariance to rotation achieved by the group convolutional neural network. So this is, they are the output of the positive result. So this is actually the value. And so this circle is the correct response from the neural network. And the red one is the group convolutional neural network with 8 discretization. And the green one is the standard convolutional neural network. And you can, and this one, well, circle, this picture is made by inputting the rotated images to the trained neural network. So if the network learns the rotational invariance or rotational robustness, then the output should be close to circle. And you can see that the green result is very, well, gives a very different result over the different angles. That is somehow very reasonable because the translation invariant convolutional neural network doesn't consider the rotational invariance. And in contrast, rotational convolutional neural network gives much robust output to the rotation of the testing images. So the bottom rows are more difficult task of tumor detection. So sometimes the red curve still not too close to perfect rotational invariance, but still much better than the baseline CNN. Okay, so I will talk about steerable CNN very briefly. Steerable CNN is a more advanced convolutional neural network than the group convolutional neural network. It uses group, but it uses further symmetry in the architecture. So group convolutional neural network already uses the group equivariant filter in the convolution layer. But for the channel direction, we don't use any symmetry. However, there are some cases that channel direction, meaning that the output value of the signal should satisfy some group equivariance or invariance. Here is some example. This is an example of vector field on the two-dimensional space. So at each point, we have some vector, like the flow to describe the differential equations. In this case, if we rotate the object in the ground space, then the direction of the vector in the vector field should follow some group action. That should be more natural in this case. So there are some cases that this output value, in this case, two-dimensional vector at each point, should satisfy some group action and make use of it in the architecture of the group convolutional neural network. For this purpose, these guys, this is the same group as our proposal of convolutional neural networks, Maxwell and the other people, consider the group action on the filter direction, the channel direction also. I skipped the details, but the F is a signal and the C is our index for the channel direction. For the channel direction, they apply some matrix depending on the group applied to the spatial filter here. And in this case, rotation dependent matrix is applied to the channel direction and it takes a filter after spatial translation and rotation. And this is the basic idea of a steerable convolution layer. And it works very well in practice. And here are some example. This is a rotational MNIST, as I showed in the previous slide. And the performance gain from the group convolutional neural network is very nice. And they show their very small test error for rotational MNIST. And well, I go over very quickly, but this is our electron microscopy images, and there is a segmentation challenge in some conference, and the the steerable group convolutional neural network shows one of the top 10 performers in the competition, and you can see that in the leaderboard, the proposed method of using the group steerable convolutional neural network shows the third position. So it's a very competitive in comparison with the state of the art of this field, and the group action works very well. Okay, so I finished the part of the group convolutional neural network here, and I would like to go into the representation learning using the group representation. So I'm going to talk about the group representation in more details and the connection to Fourier transform. Okay, I have already defined the group representation as a linear action on the vector space of group, and we can consider the isomorphic group representation. To define it, I first introduce some linear mapping between the group representation. It is called G linear map or G map. So let's say that we have two representations of the same group, and here's one group representation, rho, and the rho prime is another one. And so we have for specific G, we have two linear mapping. One is V to V, and one is V prime to V prime. And G linear is a mapping from vector space V to another vector space V prime. And if this diagram commutes, we say that T is a G linear map. This is a kind of the mapping from one representation to another. Okay, so if G map T is invertible, which means that this is isomorphism of the vector space, obviously, but invertible, linear mapping is invertible only if V and V prime have the same dimensionality, and the injective and surjective. And then this is called isomorphism of G map between the two group representations. And if there is an isomorphism, we say that the two representations are isomorphic. And we can discuss the decomposition of representation, expressing one representation to a direct product, in some sense, direct product of many representations. Okay, so the direct sum of many representations. That means that in terms of matrices, to express a representation mapping, we can have a simultaneous block diagonalization. I will explain the meaning later. At first point, let's define the sub-representations. Suppose that we have a representation, rho V, and W is a subspace, so that rho is invariant, W is invariant with respect to any rho of G, any G, for any G. Then we can define our new representation by restricting V to the subspace W, right? Okay, in this restriction is called sub-representation of rho V. In the matrix form, if we can find the appropriate basis of V, we can express the matrix in this form. This part should be 0. Because if we plug the element in the subspace W0 in this case, this second part should be 0 because of this restriction condition of the definition. So this part can be 0. And the important notion about decomposition is reducibility. A representation is reducible if there is non-trivial sub-representation. Non-trivial means that the space is not 0 or the whole entire space. If there is a non-trivial sub-representation, that's called reducible. If not, that's called irreducible. So irreducible representation doesn't have any non-trivial sub-representation. Okay, so in another sense, well, in another way, the irreducible representation is the most basic representation which doesn't be decomposed further. Okay, we can define the direct product of a representation. That's a straightforward definition. We make a direct product of the vector space and the direct product of the representation. That's it. And this is a very famous theorem about the finite group. Let's consider the finite dimensional representation on the finite group, meaning that the number of elements is finite. Then any sub-representation, for any sub-representation, we can find a complementary representation that gives a total original representation as a direct sum of the two representations. This means in terms of the matrix, the sub-representation can give this type of formulation, matrix expression. But the Mashket's theorem tells that for finite group, we can make it block diagonalized. You may think that this is obvious, that unless this part is non-zero, but well, consider that this must be block diagonalized irrespective to element G. So we have many matrices actually, depending on G. But by block diagonalization, we need to find a fixed basis which is not dependent, which doesn't depend on G, that gives block diagonalization for all elements of G, all matrices depending on G. That's the meaning of this block diagonalization. So this is much, much stronger than the block diagonalization for the single matrix. That's always possible if they are invertible. Okay, so it is known that for some groups, this type of block diagonalization is always possible. And the Mashket's theorem is one of them. So for finite group, any finite dimensional representation can be expressed as a direct sum of irreducible representations. So this is, in matrix terminology, the simultaneous block diagonalization. Simultaneous means that the block diagonalization can be achieved irrespective for G. Doesn't depend on G. We can find a basis, change of basis, which doesn't depend on G. So this is very strong results. Also, for, I'm not defining the locally compact abelian group, but let's say that the abelian group like SO2, this is a two-dimensional rotation, this is abelian. Locally compact abelian group also satisfies this completely reducible property. And also the compact Lie group, which the example of this one is orthogonal group and the special orthogonal group, they also satisfy this completely reducibility. So we can always, for any representation, we can always, for any finite dimensional representation, we can always find the fixed basis irrespective to G that realize the block diagonalization. And each block corresponds to irreducible representation. Okay, here's some example. So this is again the example of a symmetric group S3, and we can see we have already seen this two-dimensional representation. So I call it, well, the popular name for this is standard representation. And this is basically illustrating this picture, this figure. And another simple representation is given by this one-dimensional representation. This is one-dimensional representation, meaning that this is just a scalar value. And one-dimensional space like R is considered as a vector space. And anyway, this is just a scalar. And the group action, sorry, the group multiplication should be split into the multiplication of this scalar. And this is the sign of G, meaning that there is a for any element of symmetric group can be given by the multiplication of the pairwise permutation. And if the number of pairwise permutation is odd, we assign this one -1. And if this is even, we assign this value +1, sorry. And it is known that this reflection, because reflection is a swap of two elements, this value is -1. So if we have a reflection, then this is -1. If we don't need to use reflection, then this is +1. And it is easy to see that this gives a group representation by definition. And this is called alternating representation. And we have always the trivial representation. This is a one-dimensional representation assigning all the elements to 1. This is identity mapping of one-dimensional vector space. And it is known, so the one-dimensional representation is always irreducible because we cannot decompose the one-dimensional space into 2, right? And also, it is obvious that this two-dimensional representation is irreducible because this is rotation. We cannot find any one-dimensional space which is invariant to this group, the linear transforms. So they are the example of irreducible representation of S3. And I don't show the proof of this, but it is known that these 3 irreducible representations are all the reducible representation of S3. So they are all the irreducible representation. Okay, so I'm going to explain the Fourier transform in connection with irreducible representations. And I apply these operators to make a representation learning. Okay, first, review the classical discrete Fourier transform. So the Fourier transform is on the discrete Fourier transform is defined on this discrete space which may be considered as well, this is a little bit fancy notations, but this can be regarded as a cyclic group, sorry. Yeah. With the shift, the last element will become the first element. And so this can be regarded as a cyclic group, as I explained in the middle. And the Fourier transform is simply take the inner product between this type of function and the function value at n k over n. This is a very standard definition of Fourier transform. And the Fourier inversion is also possible. In this case, this part is not the conjugate, but this function itself. And it is well known that this inversion gives back to the original signal value. Maybe I forget about some normalization factor here. This, we need to notice that, so we can see that this discrete points can be regarded as a group. So I should have included in the figure, but this is can be identified with points on the unit circle on the complex plane. And this makes an additive group. And in fact, this function here, used in defining the Fourier transform, has a special meaning. I will explain in the next slide. And at this point, we should note the equivariance relation for the Fourier transform. If you are familiar to the Fourier transform, you may have heard that the Fourier transform of the shift has a very special expression. In fact, Fourier transform of the shift is equal to the multiplication of this function to the Fourier transform of the original unshifted function. And we can see that this is a kind of matrix multiplication in this way, if we expand this one as a matrix form. And also, this matrix form can be regarded as the group action of this endpoint on the unit circle to the vector given by the Fourier transform of the original f. In that sense, if this action is denoted by, in this way, L sub A over n, we can see this is exactly the equivalence relation of Fourier transform to the additive group of on the unit circle of endpoints. Okay? So the bottom line is that Fourier transform is one very famous example that gives the equivariance relation to the group action of translation. Actually, this equivariance relation and the Fourier transform can be extended to more general group. And that's the class of locally compact abelian groups. I am not going to explain the meaning of locally compact here. This is the topological group, so the topology is locally compact. But let's just consider the abelian group, and finite abelian groups always satisfy locally compactness or compactness. And so for the abelian group, we can easily extend the Fourier theory to the group case. In that case, what is our frequency for the groups? That's an important question. Actually, the irreducible representation works as a frequency in the standard Fourier transform. So here is a very famous theorem about the irreducible representation of abelian group. Let's say that we are considering the representation of C vector space, the complex vector space. In that case, any irreducible representation on the abelian group is one-dimensional. One-dimensional is always irreducible, but in the case of abelian group, the converse is also true. Any irreducible representation is one-dimensional. And let's say that we have such irreducible recomposition for the group G. And because this is one-dimensional linear transform, this is basically the scalar value. So irreducible representation of abelian group is a function, C-valued, complex valued function on the group. Actually, in the case of Zn here, the irreducible representation is given by the Fourier kernel. So that's why I answered this question. The irreducible representation serves as a frequency. So instead of using frequency for the general class of groups, we can use the irreducible representation as a Fourier kernel to define the Fourier transform. Okay, let's use this as a definition of Fourier transform. We have all the reducible representation here, indexed by n, and this is a function of g, and it takes a complex conjugate, and it takes the inner product with f. This gives some series of complex values, and this is a Fourier transform for the general case. Quite similar to the standard Fourier transforms, right? And the Fourier inversion formula is also satisfied. If we multiply this series with the irreducible representation indexed by n, then this summation gives the original function f of g. This is again the quite straightforward the generalization of the Fourier inversion formula of the standard case. And also, it is very easy to check that this general Fourier transform is equivalent to the shift of group. In this case, shift by the group element G is defined by this, the regular representation, right? This is just a shift of function. And if we apply Fourier transform after shifting the function, then the result is the multiplication of these scalar values to the Fourier sequence. This is again the very straightforward generalization of the standard Fourier theory. The Fourier transform of the shift is just a scalar multiplication of each value of the Fourier transform. So, and so if this multiplication is considered as a group action, this is actually the group action of the vectors given by the Fourier transform, then we can say that the Fourier transform is equivalent to the group action given by the shift or translation by the group element. So Fourier transform in general, in the case of group case, the Fourier transform is the translation equivariant. And more generally, we can make if you are familiar to the Fourier transform theory, then you may know that the Fourier transform of the convolution is given by the value multiplication of the Fourier images. And this is actually the special case of this convolution and the Fourier relation, but I skip the details here. Okay, so this is important in building the representation learning using the Fourier transform in the general sense. Okay, so I'm going to explain the representation learning as the last topic of my lecture. And this part is somehow the more like the research work of ourselves. And so I cannot explain every detail of the theoretical derivation, but I want to convey some basic idea behind the papers. And this is our this part explains basically the two papers of myself and other colleagues. And we use group action to make our representation learning. Okay, I shift the topic to the representation learning. So as you may know that the representation learning is a very the important topic in recent machine learning, and deep learning is, well, expected to provide a nice representation in the layer output, and which should be effective to various downstream tasks like classification and other things. And another thing is that group action is also very important to consider the representation learning. So here's some, well, picture given by some, sorry, that this depicts the human gait. And you may see that the human gait is very periodic. In another sense, this may be given by some group action periodically. Of course, we cannot describe such a group action very explicitly, but it may be natural to imagine some group action behind the gait motion to make such periodic motion. And if we assume some group action behind, then such type of, well, the group action should be very useful in extracting the representation of the data. In this case, so the gait action is somehow a periodic, but very complicated also. But the representation, assuming some group action applied periodically, should be useful in extracting the representation behind. So based on this idea, we are considering the representation learning based on group action. Another important topic in representation learning is decomposition or disentanglement of the representation. Disentanglement is a kind of, well, the decomposition of the representation into meaningful factors. And people think it preferable because it carries easier interpretation of the representation. And also, it should be easier to control of each factor. So aim of our representation learning is to make a decomposed representation using group action. And for this purpose, we use the decomposition theorem of the representation into irreducible representations. That's a very big picture of what we are doing. So I give the very the general problem setting here. So I assume that some group is acting on the data space X. X is the data space, and some group G is acting on that. And we have an observation of data points and another data points applied by some group action given by G. And assumption is that we have a paired data, or we have a sequence of such data, and well, extract information from the paired data of a sequence of data. That's a basic idea. And for such, well, the general problem setting, in such general problem setting, we can extract the information of group action from data. And for extracting the group action, we are expecting to see some meaningful data structure, or meaningful data structure in the sequence of data or group action from the data. And one important thing is that we may not assume the knowledge about the group G or element G driving to make the group, the paired data or sequence. And there are various knowledge levels on such group G or the element small g. And in some cases, starting from the next slide, we do not assume any knowledge about the group G or element small g. The assumption is simply some group, some unknown group is acting on the space, and that drives the sequence. Even in such cases, knowing that such sequence is driven by a group, we can extract some useful information. Okay, here's some motivation of our research. So I have talked about lots about group convolutional neural network and data augmentation somehow, but for such popular approaches to the group equivariance, we always assume that the group is known, such as rotation or translations. However, there are some cases that we cannot assume such explicit application of group action on the data space. Here are a couple of examples. From these two pictures, you can easily imagine that the car in the image is rotating. And because the background is fixed, you may see that this is rotated on the turntable, for example. But this is not saying that rotation on the two-dimensional space is applied to this data, image data. Let's see that the background is fixed and the car image is not rotated. Some unseen side panel appears in the right image, right? So this is not the application of the rotation SO2 on the image, but we automatically imagine some latent three-dimensional structure in our brain and rotate the car in the brain. So this is not the explicit application of group action to the image. Another example is here. This is the image, well, with some constant translations. However, as you can see, the image is skewed in the right panel. Actually, this is synthesized by the fish lens. So the target object is moving at a constant speed, or the camera is moving at a constant speed. But because of the nonlinearity of the fish lens, the image is skewed as the object moves. That means that the translation is not directly applied to the image, but some nonlinearity is involved in the shift. And that is not, well, directly, well, the traditional convolutional neural network is not directly applicable because they assume that the data is shifted by the fixed amount. But this is not. And so we apply the group representation theory for this purpose. And we use equivariance as a constraint over the learning method. So I mainly explained the hardest setting of the unknown G or unknown group element small g. So we call it unsupervised learning of equivariant structure. Instead of this lack of knowledge, we assume that the many sequences driven by group action are observed and extract the group information from those sequences. And a generated model of the sequences is given in this way. So the group G is acting on X, but we don't know which group acts on X, or the way of action is not known either. Our assumption here is that we know some group is acting in some unknown way, very vague. However, important assumption is that for one sequence, group element small g is fixed. So the same group element is applied successfully to some starting image. In this example, this is a rotated, this is a colored rotated image. Sorry, the shift is also involved. In this case, our group is rotation, shifts, and color rotations. Color is not rotated well in some standard way, but we make some circle in the RGB three-dimensional color space and make a group in some sense, and well, the rotated color is given here. Anyway, we make some group and unknown and not used in training. But some hidden element G is applied successfully to the starting image and make this sequence. And for another sequence, another starting image and another group element are taken. We don't know that, but another sequence is given in this way. And we have a bunch of such sequences and want to extract some information. How can we do that? Basically, our approach is to consider the autoencoder for as a popular method of representation learning. And so the latent space extracts the useful information. And we have an encoder and decoder for each time slice. And they are realized by neural network, but we may not use equivariant neural network. We can use arbitrary neural network, which may not be group equivariant. And group action gives one time step. And in the latent space, we realize this transition of one time step by a linear transform. More practically, some matrix M. And because for each sequence, the group element may be different, we use a different matrix for different sequences. So each sequence has its own matrix. And anyway, this equation expresses the equivariance because the unknown group action is here. And we map phi to the latent variable. And in the latent space, the linear action is applied. And this should be commutative. And so this is explaining the equivariant constraint to the latent variable. And in practice, we use the least square as a constraint to train the encoder and the matrix M. And the second objective function is prediction or reconstruction ability. After taking the latent and apply the matrix, we then take the decoder C, and that gives original signal or the future value of the original sequence. And you can see that this is, in terms of m, this is least square of the linear factor. So we can solve m by the least square the solution. And we plug such m to this second objective function, and the autograd solves everything in the stochastic gradient descent. That's our strategy of training. Anyway, the purpose is to realize the equivariant mapping for encoder. And in that sense, and also this part is the group, the linear transform. In that sense, this matrix, which depends on the sequence, and the sequence depends on the group element G. In that sense, well, under some conditions, we can show that this mapping from group element to the matrix M in the latent space is a group representation of the unknown group G. This can be guaranteed under some conditions. And we also assume that the group representation can be decomposed into the direct sum of irreducible representations, such as the finite group or compact group, Lie groups. And if that is true, we can find the change of basis so that the matrices are simultaneously block diagonalized. So the matrix depends on G or sequence, but we can find the change of basis which doesn't depend on group element G, a fixed matrix, so that all the matrices for sequences should be expressed by the block diagonalized matrices. And this is the disentangled representation on the latent space. So there are lots of works. I haven't talked about other works on the disentangled representations, but this is the first one which uses the group theory or algebraic theory to the disentanglement for the representation learning. Okay, so we have the disentangled representation here, and I show some the experimental result regarding the representations obtained by this method. Okay, first one is not disentanglement, but we want the aim is to confirm the ability or the effectiveness of the trained representations. So basically, the representation with each data point is given by this encoder. This is a latent variable, and we use this latent variable for classification using the simple linear classifier. If this representation has the very effective information on the data, we can expect that a simple linear classification is sufficient to derive a good performance. And we use only the image of 4 in the MNIST and make a sequence, lots of sequences, and train the previous autoencoder type the model to extract the latent variable or encoder, and classify 10 classes of digit. And we compare our method with the standard representation learning, such as the SimClear or CPC, which is a standard method for the self-supervised learning. And as you can see, because we only use digit 4 for the training, our method outperforms very much in comparison to the standard self-supervised learning methods. And the second experiment is to confirm the disentangled representation. So we use a rendered image in the three-dimensional space and it takes a two-dimensional snapshot for the data. And we make a sequence of such images using the various group actions. And in this case, we applied the group action consisting of 5 types of changes like colors and the size of the object and the rotation, the orientation of the object. And after applying our method to these sequential data, and we apply the block diagonalization to all the matrices, and we see that the block diagonalization works very well to this case, and we see that there are many two-dimensional blocks as irreducible representations. And if we take each block and apply only one of the block to make the change of the latent variable, shift of the latent variable, and decode the image, then we have our sequences changing only one of the factors of 5 group factors. So for one of the blocks corresponds to, for example, the floor hue. And if we apply this matrix to change to make the sequence of latent variable and decode them, then we see that only the floor hue changes over the sequence. So this means that we can, by the group representation theory, we can extract the irreducible component which corresponds to some meaning factor of the change of the images or action of the images. So as a final topic, we want to relate this apparatus of the representation learning with a Fourier transform. Okay, let's look back on what we are doing here with our method. We are making an encoder and also decoder. And by applying some group element, which may be unknown, we see that after the change of basis by P, we have the irreducible representation matrix here. This is a generalization of this can be regarded as a generalization of classical Fourier transform, especially the shifting formula for the classical Fourier transform. If we consider the shifted data here, the encoder and plug the encoder and apply this matrix consisting of irreducible representations and apply decoder, that gives the original signal. That is what we have achieved in the previous method. And this is analogous to the standard Fourier transform. If we apply Fourier transform and some matrix consisting of the irreducible representations and apply the inverse Fourier transform, that gives a shifted function from the original one. So our objective function of the equivariant constraint gives the analogy to the classical formula for the shifted Fourier transform. So the encoder part works as a Fourier transform basically, and the decoder part works as an inverse Fourier transform. And we actually see in the experiment that for example, if we apply some nonlinear transform, we can recover the original spectrum of the signal. That's also possible. And we call this method the neural Fourier transform. And basically, in the previous method, train the phi and the psi gives a nonlinear extension of Fourier transform and inverse Fourier transform, respectively. And this is very different from the standard Fourier transform in the sense of training, because we are training training the neural network to learn Fourier transform based on data. And so this is a data-dependent Fourier transform. And for such data dependence, we can use, in the expression of the data, we can use only the meaningful frequency in the expression in the latent space. And also, our Fourier transform, neural Fourier transform, can be applied without knowing the group or group action. What we are using is the assumption that some group is acting. And equivariant constraint gives the representation expression as a representation learning. Okay, so here is the almost the last slide. And in this case, we know the group. And in the matrix M sub S, we use actually the harmonic functions for the spherical data, spherical motion, the three-dimensional rotations. In this example, we rotate some three-dimensional object to make a sequence, or in this case, actually the triplet, and take a snapshot of two-dimensional image, and use such triplet of two-dimensional images as a training data. And the constraint here is that we use our matrix here, because in this case, we assume that we know that the group is SO3, the three-dimensional rotations. We use the specialized harmonic function as an irreducible representation of M of G. And what we have trained is the encoder and decoder with the given harmonic functions in the middle. And you can see and after training, we take some testing one single two-dimensional image, which are not included in the training image, and apply this trained encoder and decoder to rotate the object in an arbitrary angle in three-dimensional space. And here are examples. And these part, well, denoted by prediction frequency, is the harmonic functions in the middle. And the final result reconstructed from the latent variable is given in the right part. And you can see that with arbitrary angle, we can rotate starting from the single two-dimensional image. This is a kind of a task of new novel view synthesis. Because of the engineering, with our image quality is not so nice, but you can see that we can rotate the three-dimensional object by the training-based neural Fourier transforms. Okay, this is almost end, and I want to wrap up my lecture. So in the first part of my talk, I gave the very basics of group theory, which are limited to the necessary topics to explain this lecture. And okay, especially I focus on the group representation, which may not be familiar to you, but this is useful to define the various machine learning methods, because this is somehow the linearization of some group structure. And as a machine learning method with group actions, I talked about the three approaches. First one is data augmentation, which is not covered in my lecture so much. And the built-in architecture. This is a group convolutional neural network. I focused on this topic in the middle. And in the last part, I talked about more recent work on the representation learning with group representation. So the group CNN realized the group invariance for the general class of groups, and satisfies equivariance relation in the group convolution layer. And it aims at a very compact representation. And the data should be low dimensional. Data can be expressed in low dimensional, and the training is also efficient, should be efficient with a low dimensional parameter representation. And in the last part of equivariant representation learning, we didn't assume we have a knowledge on group. That is a very new direction for in considering the group action. Instead, we assume that we have a paired or sequential data as an example of group action, and extract the information of group action using the group representation, which is a linear a matrix multiplication of the latent variable. And this can be regarded as a database Fourier transform, which we call neural Fourier transform. Okay, this is the end. Thank you very much.